Welcome to today's on-demand webinar about the use of Polyclar plus 730 stabilizers in beer. In this presentation, we will talk about what beer stability is, how haze is formed, and how haze is prevented. We will then talk about Polyclar plus 730 stabilizers and give you some case studies and plant trials before summarizing our work. What do we mean by drivers for beer stabilization? We want to answer the question of why should a brewery spend money to stabilize their beer? Consumers expect better quality and product consistency. The new breweries are larger with expanded distribution areas. Beer has to travel further from the brewery, and this requires beer to be stored for longer periods. There is a challenge in producing quality products in developing markets that can compete with imported beers. Domestic producers don't want imports to take over. There is also a need to reduce costs, both production costs and return beer costs. Beer is sometimes returned to the brewery if something is perceived to be wrong with it. There is also potential loss of market share from someone not having a good experience with their product. A suitable definition of beer stability is the ability of beer to resist the formation of non-biological colloidal haze. The end of useful shelf life in beer is generally considered to occur when a beer develops haze of 2 EBC. At 2 EBC units, you are visually able to perceive haze. To demonstrate the impact of environmental stress on beer, we took packaged beer and subjected it to different environmental conditions. One lot was stored cold, one lot was stored at 40 degrees Celsius, one lot was cycled between 40 and 0 degrees Celsius, 24 hours at a time, and one lot was kept at 40 degrees Celsius and also shaken at the same time. Shaking beer at high temperature produced more haze than any other storage condition. This has a lot of practical implications, particularly in countries where the summer temperatures are very warm and the beer has to travel in trucks on very bad roads. These beers will be prone to produce much more haze. The precursors for formation of haze is complexation between haze-giving polyphenols and haze-sensitive proteins. The structure of haze-sensitive protein is shown here. These proteins have high molecular weights, they are proline-rich, and originate from the Hordine fraction of malt. They transfer through the wort and finally to the beer, where they complex with the polyphenols to form haze. On the left of this slide are the monomeric polyphenol haze precursors, such as catechin and gallocatechin. These monomeric polyphenols condense to form dimers and trimers. An example of a dimer in this slide is prodelphinidin. On further oxidation, these dimers and trimers polymerize and form very large molecules called tannoids. The larger the polyphenols are in terms of molecular weight, the more polyphenolic OH groups they will have, and these OH groups then readily combine with haze-giving proteins to make protein polyphenol complexes, which will result in the formation of haze in beer. Many years ago, Chopin proposed that haze in beer is formed by protein polyphenol interaction. Carl Siebert further developed this model and noted that not all polyphenols are the same. There are haze-forming polyphenols as well as polyphenols that do not contribute to haze. Similarly, on the protein side, Siebert distinguished between haze-giving proline-rich proteins and low molecular weight foam-producing proteins. It is the proline-rich proteins that combine with the polyphenols to form haze. These polyphenols have to have at least 2 ends to combine with proteins in order to form haze. Polyphenols could have 3, 4, or 5 ends. If they don't have at least 2 ends, the chain cannot grow. We see this in haze formation where the chill haze increases with time. The longer you keep the beer warm or agitate or give any impetus to haze formation, the chill haze and total haze will increase. That's basically because these chains of proteins and polyphenols grow over time. This slide shows the O'Rourke model for haze formation. Even in very clear beer, when it is first filtered, the monomeric polyphenols combine with protein but do not contribute to haze formation. Even if the beer is absolutely clear, complexation has already begun. The reason you are not seeing haze is that the polyphenols are monomeric with small molecular weights. On oxidation, the monomeric polyphenols convert to dimers and trimers, and these combine with proteins to give you the reversible chill haze. This is the haze that appears in a bottle of beer when it's chilled and disappears when the bottle is warm, say by putting a beer on your kitchen table. On further oxidation, these dimers and trimers convert very reactive oxidized tannoids. As we saw in the previous slide, These tannoids have a number of anchoring polyphenolic OH points that make them very reactive, so they combine with protein to give you permanent haze. One thing to notice here is that the formation of permanent haze, the tannoids cross-link a number of proteins, so you get these very large tannoid protein formations. We always say that tannoids are the number one enemy of beer. For beer to be stabilized, you have to remove all the tannoids. By the same token, you have to remove about 40% of the monomeric polyphenols, which in time will give you the secondary tannoids. This slide presents some evidence for the models I've just described. For this, we did a very simple experiment. We took beer and overstabilized it with PVPP using a dose rate of 100 grams per hectoliter. At this high dose level, most of the polyphenols were absorbed out of the beer and only the haze-giving proteins were left. Then we added 3 different types of polyphenols to this beer separately: catechin, tannic acid, and oxidized catechin. Catechin is a monomeric polyphenol, tannic acid is a tannoid, and oxidized catechin represents dimeric and trimeric polyphenols. You can see on the x-axis that these were added at different dose rates. This addition produced a dose-related response for both tannic acid and oxidized catechin. We found that catechin did not give an appreciable rise in haze formation, indicating that the polyphenols have to be oxidized before they will participate in haze formation. Here you can clearly see that the red and green lines have fairly low values at 10 grams per hectoliter compared with 50 grams per hectoliter. The dose-related response is clear for both tannic acid and oxidized catechin. This is a model of haze formation showing total haze on the y-axis and storage time in weeks at an elevated temperature of 37 degrees Celsius on the x-axis. Before we did this work, we expected this graph to show only the incline phase, indicating that haze formation is directly related to storage time. However, what we found was that this graph was biphasic. There was a clear lag phase followed by a clear incline phase. During the lag phase, a large pool of tannoids is being generated. When you get a large enough amount of these very reactive tannoids in your beer, they readily combine with the haze-giving proteins to give you the incline phase. The slope of the incline phase gives you the rate of haze formation. This is the basic structure of the building block of PVPP. The important thing to note is the relation of the carbonyl group to the nitrogen. Because of their proximity, the carbonyl group has a very strong partial negative charge. This partial negative charge on the carbonyl group readily combines with beer polyphenols, which have a partial positive charge on the phenolic OH groups. The hydrogen bond between the carbonyl and the polyphenolic OH group is very strong. You can see some similarity between this structure and that of the amino acid proline. The preferential mechanism is hydrogen bonding, but there is also some evidence of pi bonding and polar interactions which further strengthen the interaction. Now we will talk specifically about Polyclar Plus 730 Stabilizer. Polyclar Plus 730 Stabilizer is a proprietary composite of micronized polyvinylpyrrolidone, commonly referred to as PVPP, and Silica Xerogel. The key features of Polyclar Plus 730 Stabilizer is that it has an optimized ratio of components for preventing chill haze and permanent haze. It has high absorptive capacity for both haze-forming protein and polyphenol precursors. Also, it has improved handling and performance characteristics. This is very important because it helps optimize the dose rate used for efficient performance. Polyclar Plus 730 Stabilizer offers simultaneous removal of haze-forming proteins, tannoids, and polyphenol precursors of tannoids all at the same time with one addition to the beer. On the handling side, the inclusion of PVPP with the silica helps to hydrate silica more efficiently and keeps the silica in suspension. This enables more efficient protein and polyphenol removal because the beer has better contact with the stabilizers due to the improved dispersion characteristics. Polyclar Plus 730 does not settle easily at the bottom of the slurry tank, which can sometimes be a problem with straight silica gel. Silica particles tend to settle and compact, while PVPP particles do not settle as readily. In the admixture of Silica Xerogel and PVPP, the PVPP component helps to redisperse the silica. This has been observed practically in breweries' slurry tanks where Polyclar Plus 730 remained in suspension and therefore provided more homogeneous dosing into the beer stream. The inclusion of PVPP in a silica slurry helps to redisperse the silica. We made 10% slurries of Silica Xerogel, PVPP, and Polyclar plus 730 stabilizer. After hydration, the slurries were poured into 100 milliliter graduated cylinders and left to stand for 24 hours. Then the graduated cylinders were stoppered and each tube was inverted back and forth until the slurries were redispersed. The results are shown in this graph. You can see that it is very easy to redisperse the Polyclar plus 730 stabilizer solution. This results in more homogeneous dosing into the beer. This graph shows the rate of sedimentation against time. The Silica Xerogel settles and compacts very rapidly compared with Polyclar plus 730 stabilizer, which does not prematurely settle. This property of Polyclar plus 730 stabilizer allows it to be dosed evenly into the beer stream so that the beer contacts with both the Silica Xerogel and the PVPP in a more homogeneous fashion. We looked at the particle size distribution of Polyclar plus 730 stabilizer and its component parts, both dry and after hydration. What we found was that the average particle size of Polyclar plus 730 stabilizer in the dry state was about 16 microns. After hydration, the average particle size of the Polyclar plus 730 was about 50 microns, 3 times as large as in the dry state, offering enhanced adsorption related to the increased surface area. This graph shows that the contact time for significant protein adsorption is about 5 minutes, at which point approximately 80% of adsorption of proteins occurs. For polyphenol adsorption, a contact time of about 10 minutes is required to maximize the removal rate of polyphenols. The red arrows indicate possible injection points for Polyclar plus 730 stabilizer. The preferred insertion point is before the inlet buffer tank. The contact time occurs in the inlet buffer tank, and then the Polyclar plus 730 is removed in the filter. Now we'll review several case studies. In our first case study, a European brewery trial, the objective was to increase product shelf life. This beer had been undergoing stabilization with 95 grams per hectoliter of Silica Xerogel. The filter run lengths were 500 hectoliters. The stabilizer was dosed in line before the primary filter for a contact time of about 10 minutes. The first test was with silica hydrogel and PVPP dosed sequentially, and the second test was of Polyclar plus 730 stabilizer. Dosing the beer with Polyclar plus 730 at 60 grams per hectoliter gave equivalent stabilization to the sequential dosing of silica hydrogel at 95 grams per hectoliter and PVPP at 20 grams per hectoliter. Polyclar plus 730 can be a cost-effective and simple stabilization option. The second case study comes from a microbrewery in the United States. The objective was to evaluate stabilization with Polyclar plus 730. 200 barrels of American lager were treated. The Polyclar plus 730 stabilizer was dosed in line before the buffer tank at a dosage rate of 10 pounds per 100 barrels, or 38.5 grams per hectoliter. At a dose rate of 10 pounds per 100 barrels, we achieved a shelf life of 5 months compared to the untreated beer, which had a shelf life of 1 month. The third case study was a trial done with a Malt-adjunct Lager. The objective was to evaluate the stabilization performance of Polyclar plus 730 stabilizer. The trial volume was 1,000 hectoliters. The stabilizer was dosed in line before the primary filter for a contact time of about 15 minutes. The criteria for stabilization was at least 6 months of shelf life. The desired results were achieved with the dose rate of 15 to 20 grams per hectoliter of Polyclar plus 730 stabilizer, producing very cost-effective stabilization for the 6-month shelf life desired. This case study involved a difficult-to-stabilize ale. We used a 2-stage stabilization approach to increase the product's shelf life. The existing stabilization regime used silica hydrogel on transfer to the maturation vessel and PVPP at filtration. To improve the shelf life, Polyclar plus 730 stabilizer at 40 grams per hectoliter was dosed on transfer from the filtration vessel to the maturation vessel. The beer was stored cold for 7 days, and then a dose of PolyclarTM stabilizer at 20 grams per hectoliter was added with the diatomaceous earth before filtration. This had a very short contact time of around 3 minutes. In Stage 1, substantial tannoid and flavonoid removal was achieved. In Stage 2, further flavonoid reduction was achieved. A heat forcing test was performed on the sample ale. It was kept at 60 degrees Celsius for 5 days and then at 0 degrees Celsius for 1 day, and the total haze was measured at 0 degrees. The stabilized product had measured a haze of 1.1 EBC after the heat forcing test, indicating a high level of haze stability. We also found that Polyclar Plus 730 Stabilizer helps with filtration performance in terms of filter pressure, filter run lengths, and beer stability. This data shows the advantages in differential pressure per hour, increased filter run lengths, and improved shelf life as indicated by total haze. Polyclar Plus 730 Stabilizer can provide prescription customizable stabilization. It selectively removes haze-causing proteins and polyphenols simultaneously with one addition. It uses existing equipment, so no capital expenditure is necessary. It is effective at lower addition rates and applicable to all types of beer. Polyclar Plus 730 has excellent handling and performance characteristics and is cost-effective. Thank you.